Today we will start energy in simple harmonic oscillation. So first we want to discuss about potential energy. We know when force acting on a particle executing simple harmonic oscillation towards its equilibrium position, it is F is equal to minus kx. F is equal to minus kx. Now, if we want to displace the particle from x is equal to 0 to x is equal to x, so we know work done W is equal to integration of 0 to x f dx, which is discussed in work power and energy chapter. So from this equation we can write F is equal to kx dx 0 to x. So why we take F is equal to kx? Because that is the force which is produced for the particle, but our applied force F is equal to will be kx, which is discussed earlier in work energy power chapter. So taking integration x dx 0 to x, so we can easily write k is equal to x square by 2 third bracket x and 0, which is half kx square. So what means all of we know potential energy EP. So that is the equation of potential energy, and we know the for simple harmonic motion equation of displacement is what? X is equal to a sine omega t plus del. So we can substitute the value half k a square sine square omega t plus del. So that is the equation of potential energy executing simple harmonic motion. Now we also know that what? K by m is equal to omega square. So k is equal to m omega square. So we can write EP is equal to half m omega square a square sine square omega t plus del. So this is also the equation of potential energy of a particle executing simple harmonic motion. Now we want to discuss about kinetic energy of a particle executing simple harmonic motion. See, what is equation of kinetic energy? All of we know the equation of kinetic energy is Ek is equal to half mv square. We know the equation of velocity is a omega cos omega t plus del. So just substitute the value half a square omega square cos square omega t plus del. Now we can write m, here we have a m omega square means k, half k square cos square omega t plus del. So that is the equation of kinetic energy of a particle. This one also. So this two are equation of kinetic energy of a particle executing simple harmonic motion. We can also express the equation of kinetic energy in another way, because we also know the equation of V is also omega root over a square minus h square. So we can also express the equation of velocity ek half m v means omega root over a square minus x square whole square. So we can substitute the value m omega square x square minus x square. So that is the another equation of kinetic energy. So this one and this one is the equation of kinetic energy of a particle executing simple harmonic motion. Now we want to determine total energy. Total energy is E, which is EP plus EK, potential energy plus kinetic energy. If you substitute the values of potential energy and kinetic energy, potential energy is half K a square sin square omega t plus del, taking common ka square from both, cos square omega t plus del, sin square theta plus cos square theta is equal to 1. So finally the total energy will be half ka square. So we can clearly see that the total energy is constant, because k is constant, a is constant, half is constant. So that is the total energy of a particle executing simple harmonic motion. And if we take half k, so half and k constant, so we can also say that the total energy is directly proportional to amplitude square. So that is the energy of a particle executing simple harmonic motion. Now if you see the equation of potential energy, you will see it contain sin square. So the graph of potential energy will be like that. Here it is time and here it will be potential energy. And as there is no minus term, because if there is a minus value after squaring it become plus, so there is no graph below the x-axis, sorry, below the below the x-axis, and there is the kinetic energy graph. Just it will start, as it contain cos square, just it will start from that portion. Yes, that is the kinetic energy graph, time and Ek. So that is all about energy of a particle executing simple harmonic motion. Thank you very much. Now if we want to see total mechanical energy in one graph, that's mean if we want to see potential energy and kinetic energy in one graph, so what we will see here? We see here that when the potential energy is maximum, the kinetic energy is minimum, and when the kinetic energy is minimum, the potential energy is maximum, because the kinetic energy contain cos square term, where cos maximum, sin minimum, and where sin minimum, their cost maximum, because sine 0 is 0 but cos 0 is 1. So from the graph we can clearly see that the total mechanical energy is constant, and where one quantity is maximum, another quantity is minimum. Okay.